Yo, what's up, everybody? Here's our Unit 5 review, and I'll try to make it as quick as possible. First question says, the first derivative is given by f prime equals, and how many critical values are there? So what I would like you guys to do is see critical values, and I want you to think f prime equals 0 or f prime does not exist. So that's the first thing that should pop into your head. And this is a calculator question. So I went to Desmos, and I graphed that, and it looks like this fella down here. And so I want to know where this is supposed to be f prime, but I couldn't put a prime there, otherwise it would do the derivative of that on Desmos. So, or something weird, I don't really know. Anyway, so this is f prime, and I plotted it in Desmos, and here we go. So critical points, I know I need f prime to equal 0 or does not exist. And this is a graph of f prime. So I don't see any places where there's any times where this graph f prime doesn't exist. So let's find all the places where this graph f prime equals 0. That's a 1, that's a 2, a 3, a 4, and I zoomed in real good so I could see a 5 and a 6. So there's 6 times where f prime equals 0, meaning there's 6 critical points. So there's 6 critical points. Fantastic. The next one was also a calculator question, and again, we're given a graph of f prime, and we want to find where f prime has a relative minimum. So we should be looking at that, and you should be instantly thinking, relative minimum, okay, f prime is going to change from a negative to a positive. Okay, relative minimum, that's what happens. F prime changing from a negative to a positive. So I graphed it on Desmos. Here it is right here. Here's a graph of f prime. And I see f prime is negative, negative, and then changes to a positive right here. And if you are on Desmos, you just click the point, and it says 0.567. Oh, gosh. So at x equals point this number. F has a relative minimum. Awesome. Looks like F would have a relative maximum. I know it didn't ask for that. Over here at whatever this point is, because F prime is changing from a positive to a negative. So this point over here would be a relative max. All right. So cool. 2 done. Let's go. Up next, this one deals with, this is probably the most confusing question on the whole thing. It's going to be dealing with our theorems. The first one talks about a maximum value. So that makes me think of the extreme value theorem, which guarantees that I'm going to have an absolute maximum and an absolute minimum if the function is continuous on a closed interval. So am I going to have a maximum value? Yes. True. Why? Because the EVT says I'm guaranteed a maximum and a minimum if the function's continuous on a closed interval. Up next, I got another closed interval. There must exist a value c where f of c equals 0. Now, guaranteeing that a value for f is going to exist based on our knowledge of f, well, that's IVT. Okay, we're not dealing with derivatives. We're not going from one level to the next as far as like derivative f to f prime. No, we're all on the same level. We're comparing an f value of 0 to these f values that I have up here. So based on the knowledge that I see here, I have f of 4 equals 3 and f of 6 equals 23. Are we guaranteed to pass through 0? We're not. If either one of these was a negative number, then I would have to pass through 0 to change from a negative to a positive, but that didn't happen. So it deals with IVT, and IVT does not guarantee that we'll have an f of c equal to 0. Up next, there must exist the value of f prime. So because we're going from knowledge of f up top to asking a question about f prime, that's going to be MVT. All right. And so if I want to look at that, I need to think about the average rate of change. MVT says f prime of c equals the average rate of change. So I'll have to look at the average rate of change on the interval of -4 to 10. And the average rate of change from -4 to 10 would be f of 6 minus f of -4 over 6 minus -4. The outputs at 6 and -4 are 23 and 3. And 6 minus -4 is 10. So that's 20 over 10. So I'm guaranteed f prime at some point C. I'm guaranteed that f prime will equal 2. Oh, cool. So this one would be true. It's also an MVT. But I'm not guaranteed that f prime is going to equal 0. So I'm going to have to put a false for that one. And I just realized that I skipped C. Oops. C, again, was the IVT problem. And are we guaranteed to pass through 10? So from a height of 3 to a height of 23, I must have passed through 10 on the way, because 10 is between 3 and 23. All right, guys, so that was all about theorems. We had our extreme value theorem, our IVT, intermediate value theorem, our MVT, mean value theorem. And the next one's going to be about, is f strictly increasing? I don't know. Does it say that? It doesn't say that. I know that that somehow f is increasing, but is it only increasing? I don't know. There's not enough information there to tell me that. If it said f prime is always greater than 0, then I'm like, yeah, f is always increasing. But it doesn't say that, so I can't assume that. The next one says that f prime exists. F prime exists, and I know that's true based on this word right here. And if that word wasn't there, I wouldn't have been able to use the mean value theorem for part D and E, because for mean value theorem to work, the function has to be differentiable, which means f prime exists. Cool, cool. Well, speaking of MVT, check out this next one. Now, remember, MVT says that my derivative is going to be guaranteed to be equal to my average rate of change at some point. So what we're going to do is we're going to find our secant line. Our average rate of change is the slope of that secant line. And I'm going to say, hey, so that's our slope of our secant. I'm going to say, hey, is there any time where f prime is equal to that? And hopefully in this class we understand, and we already know, that f prime is synonymous with the slope of the tangent. So I'm going to imagine a tangent line and on the interval, and my tangent line here would be too steep. My tangent line on this section would be negative, but somewhere between there, maybe like right about here-ish, if I drew the tangent line, it would have the same slope as that red secant line. And I can think about that tangent line moving, and then about right here, that tangent line would have the same slope as the secant line again. So based on this graph, it looks like there's two places where the slope of the tangent is equal to the slope of the secant. So how many times is the mean value theorem satisfied? A 1, a 2. So there's two locations where the derivative is equal to the average rate of change. All right, up next, this is the fun problem. It's always easier than it looks here. So we're comparing f of 1 to f prime of 1 to f double prime of 1. So f of 1 is pretty self-explanatory. It's the value at 1. Well, the value at 1 is 0. F prime of 1, well, I'm not going to have an exact number for that, but I do know that f is increasing. So since f is increasing, f prime is greater than 0. Cool, cool. So I know that f prime is a positive number. And then my second derivative, well, I could think about the concavity of f, and f is concave down, like a frown. So I know that f double prime is less than 0. It's a negative. So if I had to list those in ascending order, well, I'd say the smallest one was f double prime. And then the next smallest would be f, because that was 0. While the biggest one had to be the f prime, because that was the only one that was positive. All right, the next problem, we got 5 different tables to look at. And it tells us that f prime of 3 equals 2. So the instantaneous rate of change at x equals 3 needs to be 2. And it also tells me that the second derivative is going to be negative. So I'm going to have to look at the first rate of change to see about that guy. And I'll have to look at the second rate of change. All right, so first up, let's look at our first derivative, or our first differences. This is a difference of 2, a difference of 2, and a difference of 2. So it does meet the first requirement, but the second differences, or the second derivative, is 0 and 0. So we don't meet the second requirement. So while the first derivative worked out nicely, the second derivative didn't. Let's take a look at the second one. All right, my first change is a decrease of 2.5. Oh, sorry, increase of 2.5, and an increase of 2. So that means right at this moment will be a difference somewhere between the two. So I would expect f prime of 3 to be between 2 and 2.5, probably about 2 1/4. So this doesn't really meet the first requirement. Let's check the next table. The next table has a difference of 2 here. That looks good. And then a difference of 1.5 here. So right at x equals 3, f prime is somewhere between 2 and 1.5. So it's like 1.75. So that table's not working for me either. If I look at the next one, I've got a difference of 2.5. I've got a difference of, what is that? 1.5. So right at x equals 3, my f prime is somewhere between 2.5 and 1.5. Hey, it's about 2. So we do meet the first requirement. Let's check out the second one. Let's look at the second differences. So the second differences, went from 2.5 to 1.5, so it went down by 1, and then from 1.5 to 0.5, so it went down by 1 again. Oh, so our second differences are negative, so our second derivative is less than 0. So this table meets all the requirements. It is the winner, winner, chicken dinner. Up next, we're finding the inflection points. So inflection points means that f double prime is going to be changing signs. Changes signs. So the first thing I need to do is find the second derivative. So y prime equals 6x squared minus 12x. Y double prime equals 12x minus 12. So I found the second derivative. Now let's see where that second derivative equals 0. So I can make my sign chart. I can factor out the 12. That leaves me with x minus 1. And my solution is going to be x equals 1. So I could have a inflection point at x equals 1. So I'll make a sign chart. And this is a sign chart for the second derivative because I'm looking for inflection points. And my possible inflection point is at x equals 1. So I'm going to pick a test point on the left side of 1. Let's try 0. If I threw a 0 in this second derivative, well, that would be 12 times negative 1. That would be a negative number. And then if I had used a test point of, say, 2, well, in the second derivative, a 2 would give me a positive output. So from this sign chart, I can see that since my second derivative is negative from negative infinity to 1, I would say that f is concave down. And then after 1, f is concave up. So that means I have an inflection point at x equals 1 because f double prime changes from a negative to positive. So I have an inflection point at x equals 1 because f double prime changes negative to positive. So we're supposed to be as specific as possible in our answer. On the next one, same deal. My first derivative is 8x cubed minus 8. And then my second derivative is 24x squared. So to find an inflection point, I'm going to make a sign chart. I need to know where the second derivative equals 0. Well, that'll be when x equals 0. So my sign chart for f double prime, I'll pick a point to the left, so say -1. If I threw a -1 in my second derivative, that would be -1 squared, so it would spit out a positive. If I threw a +1, the right side of 0, it would also spit out a positive. So even though the second derivative was equal to 0, the second derivative never changed signs. So I know that f is concave up forever. So there's no inflection point here. And the reason is because f double prime never changed signs. No sign change for f double prime. All right, up next, we have a mean value theorem question. So cool. First, I need to determine is f continuous and differentiable on 2 to 5? On 2 to 5, yeah, that function is continuous and differentiable. If you're not sure, it's got a horizontal shift right 1, and the graph would look a little something like that. Yeah, so we can use mean value theorem. Mean value theorem says f prime of c equals the average rate of change f of b minus f of a over b minus a. And let's start by finding the average rate of change. So that would be f of 5 minus f of 2 over 5 minus 2. Let's plug that 5 and that 2 in there. When I plug a 5 in, I get the square root of 4, which is 2. When I plug that 2 in, I get the square root of 1, which is 1. So I get 1 over 3 for my average rate of change. For f prime, we got to do the derivative. So the derivative of a square root is 1 over 2 square root of stuff. So I should be thinking about chain rule, but this one's easy because the derivative of my baby is just 1. So if I'm thinking chain rule, I'm multiplying by the derivative of the inner function. It's just 1. No biggie. All right, so let's skip a little. There we go. So mean value theorem says that my f prime, this guy right here, has to equal 1/3. So let's solve that. And when I have two fractions like that, I'm just going to do the reciprocal of both of them. So I'll do, there you go, just like flipping over both the fractions. And we'll solve this, divide by 2, square both sides, and then add 1. So 9/4 plus 1, 9/4 plus 4/4 is 13/4. All right, so that one actually had a little bit of algebra to it. Up next, we're finding the maximum and minimum values. So think extreme value theorem. Our max and min could come from the endpoints or the critical points. So I'm going to start this by looking for the critical points where f prime equals 0 or does not exist. There's my f prime. F prime equals 0 at x equals 5. So there's my critical point, and So I have to compare that to the values on the endpoints as well. So remember, extreme value theorem says I have to plug it back into the original function and just see who's the biggest, who's the smallest. I got my endpoints. I've got my critical point. We're plugging those back into the original function. So it's going to be a little bit of work here. This is going to be negative 3 squared minus 10 times negative 3 plus 5. It's a 9 plus 30 plus 5. 35 plus 9. 44. All right, so I've now put a 44 for negative 3. Do the same thing with the 5. Skip a little step here. What I got? 25 minus 50 plus 5. It's a negative 25 plus 5, so negative 20. And then do the same thing with the 8. So we got 64 minus 80 plus 5. 64 minus 80 is a negative 16. Negative 16 plus 5 is a negative 11. Oof. And we're looking for the absolute max. So our absolute maximum would be at x equals negative 3. And our absolute minimum would be at x equals 5. But you know what? It says find the maximum and minimum values. So on a multiple choice test, it's really important that we read the word values and say that our maximum value is 44 and our minimum value is negative 20. Okay. On a FRQ, you're never wrong by saying that the max is at negative 3 comma 44 and that the min is at 5 comma negative 20. But on a multiple choice, it said values, so make sure you pick out the values, the y values. All right, number 40. There's my f prime. It says that f has a local maximum at x equals. So it looks like I need to make a sign chart because to have a local max, local min, I would prove either one of those by making a sign chart for f prime. All right. Well, our critical points would be x equals 0 based on that, x equals 4 based on this term, and x equals negative 3 based on that term. So negative 3, 0, and 4. All right, and we need to be seeing where f prime changes signs. So I need to think about test points. I need to pick a test point to the left of negative 3. How about negative 5? So if I use a test point of negative 5, that's going to be a positive over here. A test point of negative 5 is going to be a positive over here because it's going to get squared. And test point of negative 5 is going to be a negative here. So positive times a negative is going to be a negative. Now I'm going to use a little shortcut here. I'm going to ask, do I expect the sign to change at x equals negative 3? So the negative 3 came from that factor, which does not have an even multiplicity, so I do expect the sign to change. At x equals 0, that sucker gets squared, so I don't expect the sign to change. And at x equals 4, I see another even multiplicity, so I don't expect the sign to change. So my sign chart's going to look like that, negative, positive, positive, positive. So do I have a local maximum at x equals 4? No, I don't, because our sign went from positive to positive, so that's false. F has a local minimum at x equals negative 3. That's true because f prime changed from a negative to positive. And f has neither a local max nor min at x equals 0. That's also true because there's no sign change, so that would be a neither. So we got a false, true, true. All right, this one's pretty cool. Number 41 says that I got some values for f prime and f double prime. Identify a relative minimum or maximum. Cool. Well, it's going to start by picking out the critical points. Our critical points are at x equals, thank you, are at x equals negative 4 and at x equals 3. The reason those are critical points is because the f prime was equal to 0. So because f prime was equal to 0, I know that that's a critical point and that's a critical point. So now we're going to look at the second derivative, and this is called the second derivative test. So at those critical points, take a look at the second derivative. At x equals -4, the second derivative is positive, meaning that the function is concave up at that point. At x equals 3, the second derivative is negative, so the function's concave down at that critical point. So at x equals -4, I drew a little concave up function and a critical point, and I could see that that would be a minimum. And the reason would be because at that critical point, the second derivative is positive. So it's concave up, f is concave up, therefore that critical point is a minimum. The opposite is true at x equals 3. At x equals 3, we have a relative maximum, and that's because the second derivative is negative. And you really should draw these, like, or make the function with your hand. So you don't have to memorize as much. You can just be like, all right, it's a critical point, and f is concave up. Well, if f is concave up, that's a minimum. Okay. Easy to do just by looking at your hand and thinking of concave up versus concave down. All right, up next, I've got a graph of f, and I've got to pick out the graph of the derivative. So I've got to pick out the graph of f prime. Well, I see that f has 1, 2, 3 horizontal tangents, three critical points. So I'm looking for f prime to equal 0, a 1, a 2, a 3 times. There you go. A relative minimum. So I should see f prime changing from negative to positive, then positive to negative because that's a relative maximum, and then from negative to positive again because we have another relative minimum. All right, up next, there's supposed to be a graph that goes with this. Thank you. But I don't have the graph, and I don't need it. Look at the multiplicities. No multiplicity, so I know f double prime is going to change signs there. No multiplicity, so I know that f double prime is going to change signs there. Even multiplicity, at x equals b, f double prime is not changing signs. So the only place we change signs is at x equals 0 and x equals a. So a is the correct answer, and I didn't even need the graph that went with it. Last up. All right, which of the following statements must be true? F has well, this is a graph of f prime. And f prime is changing from a negative to a positive, and then from a positive to a negative. And I also see that f prime is changing directions here. So we can talk about relative extrema and some other stuff. F has a relative minimum at x equals -3. X equals -3. That's true because f prime changes from a negative to a positive. So that's a true. Up next, it says that f has a point of inflection. So point of inflection on a graph of f prime would look like a change from increasing to decreasing or decreasing to increasing. So a change in direction. F prime changes direction. That's the one that's often forgotten. And it looks like we have a change in direction for f prime right here at x equals 0. Oh, snap. But not at x equals -2. Bye-bye. The graph has exactly one point of inflection. Yes, at x equals 0, f prime changes its direction. So that's another true statement. So we like 1, we like 3. And it says the graph of f is concave down. Again, this is often forgotten. If f is concave down, then f prime is decreasing. And is f prime decreasing from 0 to 4? Yes, it is. So another true statement done.